What's up, everybody? It's Chris, back again with another Chem 1B video. Today we're going to go over osmotic pressure and the Van't Hoff factor. So, example problem 1 reads, the following pairs of aqueous solutions are separated by a semi-permeable membrane. In which direction will the solvent flow? And then it'll give you two different solutions. So, one key identification that we have to make is that the solvent is like what the solute is dissolved in. So in this case, think of water, right? Now, for the sake of organization, I'm just going to draw what the professor was using. It's basically this U-shaped beaker looking thing, and it's got the semi-permeable membrane down at the bottom. Now, I'm going to put solution A on the left and solution B on the right. So the trick to these is to take your molarity. So note, take molarity and then times it by your Van't Hoff factor. And then once we do that, we can compare both sides. So in this case, we're going to get solution A has a molarity of 3.45, and we multiply that by a Van't Hoff factor of, well, to get the Van't Hoff factor, we need to take our compound, put it in water, and then ask ourselves what happens. When you put K3PO4 into water, PO4 is a polyatomic ion, so that will dissociate on its own, PO4 minus, and then you'll have three separate K plus ions. So that means that our Van't Hoff factor is 4, all of those ions added up. So we multiply this by 4. And if we do this math, we'll get 13.8. Now, on the other side, we're going to do 3.45 and then multiply it by what will happen if we put NaCl in water. It'll only dissociate into Na plus and Cl minus. So that's 2 total ions in water. So multiply that by 2. So that means we'll get 6.9 over here. So if these water levels were equal, let's just draw a rough diagram of what the amount of particles on each side would look like. Well, you're going to have a lot more stuff going on this side, right? It's a lot more crowded than this side because this side only has 6.9. So the question is, what will happen? Now, the way I like to explain this, it may not be that great of an analogy, but think of a party. If you have a lot of people, and let's just say you have 2 houses, a big house and a small house. You're going to have a big party and a little party. Your big party with a lot of people is going to require more space. So that means if we wanted to keep it equal, the amount of square footage per person, think of it that way. If you can't think about it in terms of particles, this water will go down on this side, and then it'll go up on this side. And in an effort to give this crowded left side more space and the spacious right side enough space so that it's equivalent to the left side. So in this case, we're going to have a shift from B to A. So your answer written out would be B to A. Cool. Now, example problem 2, we're going to shift directions and we're going to test a different concept here, but it reads, determine the molarity of each of the following solutions from its osmotic pressure at 35 degrees Celsius. And it gives you the osmotic pressure is 0.605 atm for a solution of CaCl2. Also, totally ignore each of the following. We're going to only be doing one problem for the sake of time. So we know that we actually have a equation for this. And our equation goes pi equals I m r t, such that I is our Van't Hoff factor, pi is our osmotic pressure, m is your molarity, r is a constant, so r equals 0.0821, and the units on that is liters times atm over Kelvin times moles, and T is your temp. Now, one trick is that a lot of the problems will have the temp in Celsius, but we can't use it in Celsius when we plug it into this formula because our constant right here uses Kelvin. So we actually have to cancel that out. So let's just plug and chug now. We are given pi is 0.605 atm. And our Van't Hoff factor, well, what's going to happen when we put CaCl2 into water? You're going to get Ca and 2 Cl minus ions. So that'll give you a total of 3. And that means our I is 3. And our Van't Hoff factor actually doesn't have any units on it. Our M is what we're looking for. And we know that's in moles per liter. Our R we just plug in, 0.0821 liters times atm, K times mole. Also, let me clean up the screen a little bit. Okay, and then we're going to multiply that by our temp, which is 35 plus 273, which puts us at 308 Kelvin. Now this Kelvin will cancel with this. And if we multiply our left and right sides, well, just our right side, we'll get 0.605 atm. And that's equivalent to 75.8604. And then our constant. So this actually has a units right here of atm. So when we divide it out, it'll actually cancel, and we'll have to just divide both sides by 75.8604 atm. Our atms cancel, and that leaves us with m, which is our unknown variable, equal to 0.007975 moles per liter. Or you can write it in scientific notation as 7.98 times 10 to the negative 3. Both answers work. If you have any questions on these, feel free to drop into SI office hours. They're posted in the description below, and have a good day.